Hello and welcome. In this video, we are going to look at trigonometry. When we talk of trigonometry, we are going to look at the relationship between angles and sizes of triangles. What is then a triangle? A triangle is a plane figure bounded by three sizes and three angles. After knowing what a triangle is, let's look at the kinds of triangles. 1. We have what we call the equilateral triangle. This is a type of triangle with all the three sizes and all the three angles being equal. We also have what we call the isosceles triangle, in which two sizes and two angles are equal. Then we have the scalene triangle, where all the three sizes are unequal and all the angles are unequal. Then the last type of triangle we'll talk about will be the right-angled triangle. With the right-angled triangle, one of its angle is 90 degrees. In trigonometry, we are going to consider whether a triangle is a right-angled triangle or it is not a right-angled triangle. Let's take a look at when it is a right-angled triangle. Let's start this with an activity. And in this activity, let's draw a vertical line which measures 4 centimeters. Then a horizontal line which measures 3 centimeters. We'll realize that the meeting point of the horizontal line and the vertical line here forms an angle of 90 degrees. Now let's join the ends of these lines together to get a close figure. When we do that, this gives us a triangle, and specifically it is a right-angled triangle. Let's label them as A, B, and C. Already we said B should be 4 centimeters and C should be 3 centimeters. When we use a rule to measure A will be equal to 5 centimeters. We can repeat this activity for several values of B and C. I've done that using additional two activities, which are represented in the table here. In the table for activity 1, we realize that the value of B is 4, value of C is 3, and that of A when we measure is 5. When we square B, that gives us 16. Square C, that gives us 9. Then when we square A, that gives us 25. Now when we add B squared and C squared, that gives us 25. Let's come to the second activity. In the second activity, when B is equal to 5 and C is equal to 6, measuring A will be 7.8. That gives us B squared to be 25, C squared to be 36, a squared to be 60.8, and b squared plus c squared will be 61. Then with activity 3, where b is 12, c is 5, then measuring a becomes 13. That gives us b squared to be 144, c squared to be 25, and a squared to be 169, where b squared plus c squared will be 169 also. Now, when we consider the two columns from the table here, we'll realize that the two columns here for a squared and b squared plus c squared are the same. When we look at the second activity, where we have a squared to be 60.8, rounded to the nearest whole number gives us 61, which is equal to what we have here. So when we compare the two columns here, we'll realize that they are the same. So we can say that from the table above, the relation between A, the side A in the triangle here, is also known as the hypotenuse. So the relation between A, the hypotenuse, B and C is b squared plus c squared equal a squared. This is what we call the Pythagoras Theorem. The Pythagoras Theorem then states that in a right angled triangle, the square on the hypotenuse is equal to the sum of squares on the other two sides. Let's look at how we apply Pythagoras Theorem. Let's start with an example. In this example, if you are asked to find the value of x and y in the following diagrams, let's take the first diagram where we have the horizontal to be x, the vertical to be 8, and the hypotenuse to be 10. Then, with the help of Pythagoras Theorem, the vertical squared plus the horizontal squared should be equal to square of the hypotenuse. This gives us a relation here. Then we know that 8 squared is equal to 64, 10 squared is equal to 100. When we subtract 64 from both sides of this equation, we get x squared to be equal to 36. When we take square root of both sides, x will be equal to 6. And this is how we apply Pythagoras Theorem to find the value of x. Let's look at the second diagram, where the horizontal is now 10 centimeters, the vertical is 9 centimeters, and the hypotenuse is y. To find y, since the other two sides are given and the hypotenuse is not given, the relation is as follows. Y squared will be equal to 9 squared plus 10 squared. This means that y squared will be equal to 81 plus 100. Y squared will then be equal to 181. When we take square root of that, that gives us 13.5 centimeters. So the value of y in the second diagram is 13 centimeters by applying Pythagoras Theorem. Let's look at another example. where we are asked to find the value of u and vin in this particular diagram. In this particular diagram, we'll realize that when we consider the whole triangle ABC, it is not a right-angled triangle, but triangle ABC is divided as triangle APC and triangle PBC, which are all right-angled triangles as indicated here. So we are going to separate them and apply Pythagoras theorem to each triangle since they are right-angled triangles. So we can say that from triangle APC, the 10 here becomes our hypotenuse, then the other two sizes will be u and 6. So we can say from triangle APC, u squared plus 6 squared should be equal to 10 squared. So from triangle APC, we can say u squared plus 6 squared should be equal to 10 squared. That gives us u squared to be equal to 100 minus 36. U squared will then be equal to 64. And that gives us u to be equal to 8. Then from triangle PBC, our hypotenuse will now be 17. The horizontal will be vin and the vertical will be u. So we can say that u squared plus vin squared should be equal to 17 squared. But in this case, we know the value of u. So replacing u here, we'll have 8 squared plus vin squared to be 17 squared. 64 plus vin squared will now be equal to 289, which is 17 squared. Subtracting 64 from both sides of the equation, we have vin squared to be 225. And taking square root of both sides, vin will be equal to 15. And that gives us the value of vin. So this is how we apply Pythagoras theorem to find the values of u and vin in this particular example.